Torch. Fake quantize per channel affine. Description. This function implements per channel affine quantization for tensors. It simulates quantization by clamping the input tensor to the range 0, 255, then dividing by the scale and rounding to the nearest integer. This process is done per channel, allowing for different scales for each channel. Inputs. Input a tensor of any shape containing the values to be quantized. Scale a tensor of shape C, where C is the number of channels in the input tensor. It represents the scale factor for each channel. 0. A tensor of shape C, where C is the number of channels in the input tensor. It represents the 0 point value for each channel. Axis, an integer representing the axis to quantize over. Default is 1. Outputs. Quantized, a tensor of the same shape as the input tensor, containing the quantized values. Steps. Clamping the input tensor is clamped to the range 0, 255, effectively limiting the values to the representable range of 8-bit quantization. Scaling. The clamped values are then divided by the scale factor, which is specific to each channel. Rounding. The scaled values are rounded to the nearest integer, simulating the quantization process. 0 point adjustment. The rounded values are finally adjusted by adding the 0 point value for each channel. Challenges and fixes. Challenge 1. Inaccurate quantization due to rounding errors. Sample use case that resulted in challenge 1 when the input tensor contains values very close to the quantization boundaries. Rounding errors can lead to inaccurate quantization. Fixes to challenge 1. The scale and 0 point values should be carefully chosen to minimize the impact of rounding errors. Techniques like symmetric quantization or using a larger number of quantization levels can be employed to reduce the impact of rounding errors. Challenge 2. Performance bottlenecks due to per-channel operations. Sample use case that resulted in challenge 2. Quantizing a large tensor per channel can result in significant performance overhead, especially when the number of channels is high. Fixes to challenge 2. Efficient implementations of per-channel operations can mitigate performance bottlenecks. Optimizing the code for specific hardware architectures and leveraging SIMD instructions can improve performance. Torch. Fake quantize per tensor affine. Description. This function implements the per tensor affine quantization of an input tensor. This means that the same scale and 0 point are applied to all elements of the tensor. The scale and 0 point are calculated based on the input tensor's minimum and maximum values and the desired quantization range. The output is a quantized tensor with the same shape as the input tensor. Inputs. Input 1. Input tensor to be quantized. It should be a float tensor. Input 2. Quantmin minimum value for the quantized range. Input 3. Quantmax maximum value for the quantized range. Input 4. Scale. The scaling factor to be applied to the input. If not specified, it is calculated from the input data. Input 5. 0 point. The 0 point to be added to the input. If not specified, it is calculated from the input data. Outputs. Output 1. The quantized tensor. Output 2. Scale. The scaling factor used for the quantization. Output 3. 0 point. The 0 point used for the quantization. Steps. Step 1. Calculate the scale and 0 point based on the input tensor's minimum and maximum values and the desired quantization range. Step 2. Quantize the input tensor using the calculated scale and 0 point. Challenges and fixes. Challenge 1. Input tensor with extreme values, like very large or small numbers. This can lead to overflow or underflow issues during quantization. Sample use case that resulted in challenge 1, a tensor with a maximum value of 1010 and a minimum value of -1010. Fixes to challenge 1 use a larger quantization range to accommodate the extreme values. Ensure appropriate scaling is applied to the input tensor before quantization. Challenge 2 input tensor with a narrow range of values. This can result in a very small scale, leading to quantization errors. Sample use case that resulted in challenge 2, a tensor with a maximum value of 1 and a minimum value of -1. Fixes to challenge 2 use a smaller quantization range to reduce quantization errors. Consider using a different quantization scheme, like per channel quantization, if appropriate. Challenge 3, the input tensor has a large number of elements. This can lead to performance bottlenecks during quantization. Sample use case that resulted in challenge 3, a tensor with millions of elements. Fixes to challenge 3 use optimized implementations of the quantization function. Consider using a GPU or other specialized hardware for acceleration.